Our next speaker is Chen. Chen completed his PhD from Yale University and he is currently a JP Morgan Research Fellow in the Reinforcement Learning Program. Then,
Hi, everybody. I'm Lin. My topic today is deep neural intelligent kernel and Laplace kernel have the same RKHS, and we posted an archive preprint here. Next slide. Thank you. Okay. The main result is restricted to the sphere. Rel neural intelligent kernel and the Laplace kernel have the same RKHS, and the main tool that I use here is complex analysis. And we need to extend NTK to complex numbers. And in the figure, you can see a five-layer ReLU NTK on a complex plane. And I only illustrate the imaginary part. And the slot here is the branch cut. And let me show you how briefly how I do this. Next slide, thank you. Okay, so what's the neural intelligent kernel? Jacob 2018 found that gradient flow on a normally initialized, fully connected neural net with a linear output layer in the infinite width limit is equivalent to the kernel regression with respect to the NTK. Next slide, thank you. Okay, so first of all, we found that ReLU NTK is an actual inner product kernel, and we use U to denote the inner product between X and Y. And we have a very simple, we found a very simple expression for ReLU NTK. And it involves arc cosine kernels of degree 0 and 1. NK is the ReLU NTK with K layers. Next slide, thank you. Okay, so our high-level strategy is to compare power series coefficients of Laplace kernel and the NTK, and we use z to the nkz to denote the nth power series coefficients of the kernel k, and we will show that both NTK and Laplace kernel the power series coefficients of both kernels is n to the 3 halves. And we will use the inclusion theorem here. The RKHS of K2 is larger than K1 if there exists a constant, positive constant such that C times K2 minus K1 is a positive definite kernel. Next slide, thank you. The main tool to analyze the power series coefficients is analytic combinatorics. The philosophy is the rate of the power series on the complex plane is determined by the local asymptotic around the dominant singularities. I mean the singularity closest to 0. Next slide, thank you. Okay, so if there is only one singularity, first of all, to use this tool, first we need to show that it satisfies the kind of analytic condition. We call it delta analytic. And if we know that the asymptotic is approximately 1 minus z to the minus alpha, we know that the n's coefficient is approximately n to the alpha minus 1. And if there are multiple singularities, the influence of each dominant singularity is added up. Next slide, thank you. Okay, so we need to extend NTK, ReLU NTK to the complex plane. So we only need to extend K0 and K1 to the complex plane. And the branch cut is -1 to 1 and 1 to infinity. Next slide, thank you. So there might be some work to prove that NTK meets the analytic condition. It might be a little bit complicated. Next slide. The asymptotic around -1, 1 is pretty simple. Next slide. Yeah. So using the tools that we mentioned here, we can show that both kernels have power series coefficients of order n to the 3 halves. And using this method, we can show that the main takeaway message restricted to the sphere. ReLU NTK and Laplace kernel have the same RKHs. If you have any questions, just ask me in the breakout section. Thank you.